For my lab, I dropped a highlighter from my hand and analyzed the video on Tracker in order to figure out the position versus time. The graph ended up looking like a quadratic graph, and from that I realized that I should figure out the model position versus time on Python. That was done via calculating the gravity and the drag force and using those formulas into Python. And my result was that when gravity and drag force is taken into account as the net force, the model position versus time graph will match that of my observed graph. The principles I needed to know. First was Newton's second law, which states that force equals mass times acceleration, and acceleration therefore equals force divided by mass. And since we know that acceleration is the change in velocity divided by the change in time, we could break this formula further into finding final velocity equals initial velocity plus force of net force divided by m times change in time. Then we needed to know the weight. Weight is found by doing negative mass times gravity. This should be a W, not an F. G equals 9.8 meters per second squared. This is the constant for Earth. And we need this because when a highlighter is dropped, gravity is acting on the highlighter. And we had drag force that we needed to take into account. That is found by basically doing negative b is a constant, times velocity squared, the magnitude of that, times the normal velocity, which is there for direction. And since this was turbulent force and there was no viscosity, that is why we use this formula. This is the video I analyzed on Tracker. As you can see, it has a quadratic graph, and this is the time and this is the position of it, and it lasts for 0.534 seconds. The highlighter's mass was 0.011 kilograms. I left the position and the initial velocity the same because it was at rest when I dropped it from my hand. The delta t is small, so for accuracy, g equals 9.8, the proportionality constant, and that is going to be the same for anything that we drop on the Earth. J hat, or the direction, is only affecting the y-axis because we're dropping it. Therefore, it's just the vertical axis. The weight equals the negative mass because we're dropping it, therefore it's going on the negative y-axis, times the g times the direction. And that will also be our net force when we're just looking at the gravity. My graph looked a bit like the observed, but it's not quite there. B was found by matching the computational models and position to the observed models and position. The constant I got from that was 0.0021. In this case, we are looking at weight and drag force because that is how we will eliminate any differences between the observed model and the computational model's graphs. As you remember, drag force is negative b, the constant that we got, times the velocity's magnitude squared times normal velocity, which is needed for direction. And the net force would then be weight plus the drag force. This arrow is pointing upwards because it's showing the air resistance caused by the drag force. I did this by making arrow 2 the highlighter's position and the drag force times the arrow scale for the axis of it. When just looking at the gravitational model and the observed model, we can see that there's quite a difference, and that was probably caused because the drag force is not added into account for the net force. When we add that into account and the gravity, you can see that the observed and the gravity plus drag force lines are quite the same. There might be a little bit of difference because the b constant might not be exactly what I thought it was, or because when I was looking at the point of mass and analyzing it on Tracker, I might have not put it exactly to what it was. Terminal velocity is shown by the gravity plus drag graph. This is because at some point the drag or force resistance will equal the gravitational pull, and therefore it will stop accelerating and continue falling at a constant speed. If thrown down initially, the gravity graph will still be constant, going down linearly. However, because it's not starting at zero velocity, the gravity and drag force graph would start at a velocity greater than that, and therefore it would start leveling off and flatlining faster.